Alright, number 7, decide whether the function is an exponential growth or exponential decay function, the constant percentage rate of growth or decay. You can tell whether it's growth or decay by this number right here. As long as it's to the positive x power, if that number is less than 1, that means that we're decaying. So this is a decay. Now to figure out the percent, you have to remember that this value right here, our base, is equal to 1 plus r. Because basically we're accounting for the fact that there's 1 of whatever we're doing, and then we're adding some percentage to that. So that if it's a positive percentage, then that is a number bigger than 1. If it's a negative percentage, it's a number less than 1. So subtract the 1 from both sides to solve for r, and you get 0.124, negative 0.124, which matches our decay thing, and as a percent, that's negative 12.4%. So if we have a bacterial culture that we're looking at, yay, it's declining. That's good since it's bacteria, right? This is in general going to follow either an exponential growth or decay depending on the situation, which has a general form of this. So we know the initial population, which is A, so that's 10,000. If its population declines to 7,000, so that would be Y. We want to, and that happens 6 hours. Okay, so basically they just told us a point 6 comma 7,000. We need to find B so that we can use that to figure out how many there will be at the end of 8 hours. So we need to divide the 10,000 over and that'll give 7/10, which is 0.7. And then you take the 6th root of each side, or you could do 0.7 to the 1st power. Either way, you should be getting 0.94229-ish. Remember, on these more decimals means more accurate. Just a little decimal issue can end up really changing your answer. Now we want to use this back in our formula. So y equals 10,000 is our initial population times our decimal, and we're talking about at the end of 8 hours, so we put in 8 here. Plug all that into your calculator and you should get 6215.328, which we might round to 6215. Something like that. So on number 9, this is a logistic function that we're talking about, and we have students infected with the flu. It's modeled by this right here. What's the initial number of infected students? Remember, initial means 0, so take a 0 and put it where t is and see what happens. Well, it doesn't affect the top, or the 1 plus 39. It gives us e to the 0. E to the 0 is 1, so that's going to go away. So we have 200 over 40, which is 5. So initially we start off with 5 students infected. Now the next problem is like one of my favorites. What is the maximum number of wolves possible in the park given this function? Why, it's 900. It's always whatever that top number is, because basically that's a horizontal asymptote that our graph is going to get closer and closer to, but never quite get to. 11, we need to plug this into our calculator. Notice that it tells us that we're talking about t years after 1900, so we're actually going to plug these in as 0, 10, 20, and so on. And then the other column will be what it's supposed to be. To do this, you go to Stat, Edit, and then once it's in the table, you go to Stat, Calc, and it asks for logistic regression, which means you need to go find logistic. A lot of times people will ask me, how do I know which type of regression to use? Well, they typically tell you in the problem. If it's exponential regression, you're looking for something that looks like exponential regression. If it's logistic regression, you're looking for something that looks like logistic. If it's logarithmic, even though logistic and logarithmic start with the same three letters, they are nothing at all related. So you do not want to do like logistic regression whenever it says logarithmic. Those aren't the same. Sorry, I went off on a tangent there. So on your calculator it tells you A, B, and C, and we get 9.0528 for the top, 1 plus 10.2794 e to the negative 0.0273x.